sampling techniques and normal distribution. You guys are going to learn how to determine probabilities and values of data through normal distribution after we go over some key terms when it comes to statistics and when you are collecting data and the different types of sampling techniques that go with collecting data. Okay, so if anything, sampling techniques is probably one of the first things that I should have went over, but I had to go back to make sure, like, okay, what things am I missing from this section? Since we kind of finished up all of our descriptive statistics stuff, this kind of still is a good spot to insert in our different sampling techniques. So we're looking at our neon green paper. You are going to be taking down some definitions and things like that, so please make sure you're taking smart notes. The examples of the different types of sampling techniques, they're not written down, so you're going to have to make sure that you listen, so then that way you can have an idea of what you're going to write down for the example of each one of these sampling techniques. So let's start with some basic stuff. Okay, a census is a count or a measure of the entire population. I know you've seen the commercial of the Census 2020. They're trying to get a number for how many people are in the U.S. Okay, so that's what a census is, a measure of the entire population. A sampling is a part of the population. Okay, it's a count or it's a measure of part of the population. When you get a sample, there is such a thing called sampling error. It is the difference between the results of a sample and those of the population. Okay, so it's the difference between the result of the sample and those of the population. Let's talk about the types of samples. Okay, so there's 5 different types of samples. Okay, and I'm going to go through each one, and I'm going to provide an example of each one. Okay, so you first have your simple random sampling. Okay, simple random sampling is when each person or each member has the same chance of being selected. Okay, that's what makes it simple and it's random. For example, when Mr. Saran decides to send out an email to all the students of Lake Wales to collect information about the students, that's an example of a simple random sampling. Every student has the opportunity to participate in the survey because he emailed it to every single student.
It's like non-biased.
Right. It just everybody has an equal chance of participating in the survey. Okay. Does that make sense with simple random sampling? Now, systematic sampling is selecting at random intervals. Okay? Like every 3 people. Let's say that you wanted to collect data for your IA. You're going to stand at the door at morning meeting and you're going to collect data from every 3rd person. That's an example of systematic sampling. You have an idea in your mind, every 3rd person. Okay? That is still unbiased because you don't know who that 3rd person is going to be, but it is a systematic sampling because that's how you are collecting your information. Does that make sense? Convenience sampling. Convenience sampling is easier to select or likely to respond. Okay? Easier to select or likely to respond, hence the word convenience. Okay, and I think I spelled that wrong. Let's see, is it I first then E? Hold on. I did spell that wrong.
Am I supposed to be writing down all these examples you're giving us?
That's what I said.
I was thinking there's a whole slide that
I specifically said there is no slide. Yeah. So make sure y'all taking smart notes.
So with systematic sampling, it's
like in your mind you have a system set up for how you're going to collect your data. So every 3rd person, every 10th person.
It's like it doesn't always have to be like every 3rd person. It could be like 3rd and then like 5th and then just like.
Because in that case then that is more like that's more like a that's more like a stratified sample because it's more random. But like that systematic is like you have it is every 3rd person. So convenient sampling. Let's say you wanted to collect some data, and you decided to collect the information from the people in this classroom. Okay, that's an example of convenient sampling because they're right here, and more than likely they too have to collect data as well. Okay, so they're more likely to respond truthfully to whatever it is that you're asking, okay? And they're also easier to collect your information because you guys are all in the same class, okay?
So like selecting people that are like within your reach.
Select the people within your reach that are close to you, okay? Like when you guys collected your height and your shoe size, right? Remember when you went to some rooms, some people were like, oh, well, I'm other, when it came to like their gender or whatever. And I mean, by all means, people can be other, but they might have been doing it to give you a hard time. Or they might have said like, well, I don't know my shoe size. It's like, well, you got a flip-flop on, just slide that bad boy off and let me look at your shoe, So, but people here, when you guys came back, everybody was like, okay, let's just go through the class. I'm 5'5", size 8.5, whatever. Okay? Questions on convenience?
For Stratify/Quota, do we just put the same definition for both of them?
No, they have two. They have two sections. Yes. Like every third person. So stratified quota sampling, they have the same definition. The difference between the two is stratified is random, quota is biased. Okay, so either of the two is when you divide your population into subgroups, and each group is represented fairly. Okay, stratified is when you do it randomly. So, for example, if Ms. Dunson wanted to get some information about how students feel about dress code, right? She wants to get some freshmen, some sophomores, some juniors, some seniors. That is basically, she's dividing the school into our classes, into our grades, which would be our subgroups, and she's going to make sure that each group is fairly represented. Stratify would be, she's just going to randomly choose the 20th person on the roll, the 100th person on the roll, the 215th person on the roll. That's stratified because it's random. Bias would be if she only went into like IB classrooms, pre-IB classrooms, and she got the opinions of those students. Okay, so that's an example of quota. Quota is biased, stratified is random. But no matter what, every grade level is represented to answer a question about dress code. Let's look at some examples. Let's see if we can identify which is which. I don't expect you to write these down. They are in the video, so if you want to go back and write them down later, you can. But I just want to make sure everybody can recognize the differences between the sampling techniques and these examples here. Okay? So I want you guys to read through each example, and then I want you guys to tell me what type of sampling you think is for each of the three. Don't say it out loud. Think about it first. An annual dog show averages 3,540 visitors. The catering manager is conducting a survey to investigate the portion of visitors who will spend more than 20, was that euros?
Yes.
Yeah, euros on food and drinks at the show. He decides to survey the first 40 people through the gate. What type of sampling technique is that?
Random.
Why do you say convenience for those who say convenience?
They're all grouped right there at the gate.
They're the first ones to come, so it's not like in intervals.
It's true. It's not in intervals. It's literally like he's like, okay, the doors are about to open. Let me stand right here, and let me just get the first 40 people. You guys are right. It is convenience. Very good. Okay, this is convenience.
Would it not be like quota sample? Would it not be like systematic sampling?
It would not be systematic because systematic means that he has a system for how he's collecting his people. He's just collecting the first 40 people that walk through the door, and then that's going to be it.
Like since there's no designated interval.
Yes.
Oh, wait,
Systematic is interval based.
I'm sorry, I meant to say stratified.
But see, the thing is that he's catering for like he's catering for like a particular show, so it's not like he's getting every possible person.
Okay.
Like the first 40 people that might walk through the door might be vegetarians.
Yeah.
You know what I'm saying? Or it might be like it's not in the sense of random. In that sense, is more so just like I just need these people to figure out what I'm going to do.
Okay.
So how would that be systematic?
This would be systematic to say he decides to survey every other person who walks through the door, or every 10th person who walks through the door.
Like he has a pattern.
Like he has a pattern with how he's going to collect his information.
Oh.
In order for it to be like the quota one, would they have to say like he surveyed all of them, but then
Like it would have to be something like
maybe
everybody was sitting at a table, and then he picked out the person who sat at the 5th seat of every table. Like that would be an example of the quota sampling. A library manager is interested in the number of people using the library each day. She decides to perform a count every 28th day for 1 year starting next Monday. Systematic. What kind of gave it away?
28.
Systematic. Every 28th day. Very good. Now Mona wants to gauge the opinion of her peers on the design of the school's yearbook. She uses her own homeroom class as her sample. Okay? Because why? Right. She's just going straight to the first period, getting her people, and boom, she's done. Okay? Questions? Now let's look at normal distribution. Okay? Let's look at normal distribution. Okay? Normal distribution is another way to represent your information. Okay? It's another way to represent your information. It is represented by a bell curve that is asymptotic to your x-axis. So when you draw a normal distribution curve yourself, you should always make sure you draw in an x-axis, just like how you draw it in for a box and whisker plot. You always want to make sure you label that x-axis like you do with a box and whisker plot, but you want to make sure that your curve does not touch that x-axis. Okay? It is split into pieces, as you guys can see here. This symbol, I've showed you this symbol before, I believe. What does that mean? The mean. The mean is smack dab in the middle of your normal distribution curve. Okay? The mean also splits your data into 50% on your left-hand side and 50% on your right-hand side. A lot of stuff y'all did last year, or some previous class. Okay? So the mean splits your data into 50% on the left, 50% on the right. From there, you have your standard deviations about the mean. Okay? This first group right here, this is one standard deviation to the left of the mean. This is one standard deviation to the right of the mean, which makes up, as you guys can see on your paper, 68% of your data. 68% of your data is represented within one standard deviation of your mean. Okay? So whatever your mean is, whatever your standard deviation is, you'll either add it to your mean or subtract it from your mean to find out the interval that makes up 68% of your data. Which means that, yes, each of these pieces is 34%. Because remember, that mean splits it in half. Then you'll have your two standard deviations, okay? Two standard deviations to the left, two standard deviations to the right. On your paper, as you guys can see, that makes up 95% of your data. 95% of your data. Okay? What's half of 95%? 42.5. So that means you'll have 42.5 to the left of your mean, 42.5 to the right of your mean. And considering that this first standard deviation is 34%, how much really is between your first standard deviation and your second standard deviation? How much is that? How much lies in between here and here? Not in this darker red. How much is that?
61.
Not 61. How much lies between your first standard deviation and your second? Not 21.
Yeah, 8.5.
It would be 8.5. How'd you get 8.5?
Only 45 minus 34.
All you have to do is subtract 42.5 minus 34. That's how you get that piece in the middle. Are you sure? Yes.
Wait, where's the 42.5?
42.5 is from the mean to a second standard deviation to your right or left. I was specifically asking between one standard deviation and two standard deviations. What's that difference? And you get that by subtracting the pink from the green.
Wait a second. 14.5.
All right, so let's fix this. Half of 95 is what again?
47.5.
47.5. So if this is 47.5, then when I subtract 47.5 from 34, what do I get?
13.5.
So then between one standard deviation and two standard deviations is 13.5%. Okay? And that goes on both because this is a symmetrical graph on both. Now for three standard deviations, to the left of your mean and to the right of your mean, that makes up 99.7%. What is half of 99.7?
49.85.
Confirmation?
Yes.
Okay. So then you said, say it again.
49.85.
49.85%. That is to the left and that's to the right of your mean. So then how much lies in between the second standard deviation and the third standard deviation?
Correct. 49.85 minus 47.5 is 2.35.
2.35?
It's the last one. Yes.
Okay, 2.35 is what makes up this last little bit. You sure?
Yeah.
Okay, 2.35 makes up that last little bit. This is how your normal distribution curve breaks down. Do mind you that these are approximations, okay? About 68, about 95, about 99.7. That still leaves a little bit that's outside of three standard deviations of your mean, okay? Because your entire curve of your normal distribution makes up 100% of your data. So if three standard deviations make up about 99.7%, that leaves you with how much left over? 0.3%. That's on the outside of three standard deviations. Okay? So half of that, what's half of 0.3? 0.15. Okay? 0.15 makes up the remainder. Okay? Questions on the different properties, the percentages, the symbols on your normal distribution curve.
So that means you're going to have 0.15, but the more you go out, the closer it's going to get to zero.
Correct. The main focus is going to be between three standard deviations, though. Okay, just remember that it's 100% underneath your curve. Okay, 100%. Since we already have 99.7%, that makes up three standard deviations. So all this is 99.7%. And then there's 100% underneath a normal distribution curve. 100 minus 99.7 is what again?
0.3.
0.3. So that leaves you with 0.3% to be divided equally amongst those two pieces that remain.
Like whenever I subtracted 49.85 and I did like that minus 1.5 and I got 2.35, you actually need to divide it in half.
Because if you did 49.85 and the 47.5, you were already only looking at one side.
That's what you mean.
And is that why the curve never touches the x-axis because of that little outside?
Exactly.
So we're gonna need to make this with our data.
Yes. But you'll see some examples of the break of like how you actually create a normal distribution curve. So that way you'll see exactly what you'll be doing for your project.
Now, if it gets to 0.15 and the more it goes out, the closer it gets to 0, will it ever reach 0 at any?
Mm-mm. And that's why it's asymptotic to the x-axis.
If your histograms are skewed to like positive or negatively, will your bell curve will also be skewed.
Exactly. If your histogram is skewed, then yes, your normal distribution curve will also be skewed because they all are representative of the same type of information. So yes, I will be looking for that as well. You can look at your histogram. If you see a majority of your data is more to the left or more to the right, that means your normal distribution curve should also be the same as well. Okay?
Will it look like that just like at a different part of the x-axis? Or
Like it'll be more like this, and that's if like a histogram,
that would be negatively skewed, right?
and this will be negatively skewed.
Then we would still split it to the middle.
Hmm?
We would still split it.
Your mean will still be at that high point. Your mean will still be located there. This means the majority of your data is on that end of the x-axis then on the front. That's not that enough.
So like for instance, the median plus 2 standard deviations is not going to be like the same as median minus 2 standard deviations.
The distance between them will be the same, yes. But numerically, it will look a little different. Let's get to an example. Open up your other yellow sheet and look at example 1. I think I've labeled it correctly. It talks about the waiting times for an elevator are normally distributed. All right, with a mean of 1.5 minutes and a standard deviation of 20 seconds. Now you might need more space for this one in particular because it is a part A, B, C, and D. But you have your notebook, so if you need to write it there in your notebook, you can. So we have a mean of 1.5 minutes and a standard deviation of 20 seconds. Now, we're going to draw a normal distribution diagram to illustrate this information, clearly indicating the mean and the times within 1, 2, and 3 standard deviations of the mean. There's just one problem here. When I draw my x-axis, how am I going to label it?
Would you have it the same as like if it's median minus 3 standard deviations, that'd be like your median minus 3 times 20? Or like,
Okay, well, 1 is mean, not median.
I'm
Mean.
sorry.
But remember, you have to add your mean or add your standard deviations to your mean. But look between your mean and your standard deviation. What's the issue?
10 minutes and then seconds, yeah.
So you got to convert. You cannot have 2 different units, okay? You cannot have 2 different units. Which way are we going to convert it to?
2 seconds.
Seconds. So then we're going to label this seconds. You can elevator wait time. We're going to have our normal distribution curve. Make sure it's asymptotic to your x-axis. It shouldn't cross or touch it. Smack dab in the middle, you're going to have your
90 seconds.
mean, which is 90 seconds, because this is in seconds. So then to get 1 standard deviation, you're going to subtract 20 to get it to the left. What's 90 minus 20? To get 1 standard deviation to the right, you're going to add 20, which is 110. So 1 standard deviation, 68% of your data lies in between 70 seconds and 110 seconds. 2 standard deviations. Subtract 20 again,
And 130.
and then 130. So you can either subtract 20 again from your previous standard deviation, or you can do your mean minus 2 standard deviations. So 90 minus 2 times 20, which is 40. And then 3 standard deviations. 30, we would subtract 20 again. And then that's it. So the thing is that you guys found your mean and standard deviation for your project, correct? Your mean should be in the middle, and then whatever your standard deviation is, that's how you should get the pieces to the left and to the right of it. Okay? Double check, make sure your mean and standard deviation are correct, or then it's not correct for your normal distribution curve.
So just to start and all that, like whenever we were talking about 0.15 and like it gets closer to 0,
Mhm.
does that mean that it would get like closer to 10 seconds and closer to 170, but never fully reach 170?
That means it can be however many standard deviations after that. But you don't. The way that normal distribution curves work is you only look at 3 standard deviations. You don't go anything outside of that because you're already at over 99% of your data is there. Now, if you do have something that's less than 30 or more than 150, there's a possibility it could be an outlier. And so then, but that little piece takes care of the outlier. It's still a part of that data. Do we have a curve? All right, let's answer some questions based off of this. It asks us to find the probability that a person waits longer than 2 minutes and 10 seconds for the elevator. 2 minutes and 10 seconds is how many seconds?
130.
So really and truly, we're looking for when they wait longer than 130 seconds. So on our normal distribution curve, what that would look like is at 130, we're trying to figure out what's the probability over here. That's really what we're looking for. How many? Or what's the percentage? What's the probability? Now 130 was at the 2 standard deviation mark. And we want everything that is to the right after that. So think about your percentages that we had to fix on our original normal distribution curve. What will be the probability?
2.3.
No, because you have to add the 0.15 from the outside.
Yeah. You mean the 0.15?
Mm-hmm.
Oh, yeah, 2.4.
So is that the decimal or is that the percentage? So it would be 2.5%, but what is it as a decimal? Because it's asking me for the probability.
0.
Move it over 2. So my point and then 0.25?
Oh, yeah. That's fine.
There we go.
I don't get how you got 2.5.
Okay. So you could do this a couple of ways. One way is remember the mean splits it into 50%, right? 130 was at 2 standard deviations. And between your mean and 2 standard deviations, that was how much?
34%, 13.5.
So in total, what was that?
42.5.
You mean 47.5?
Oh, yeah, 47.
It'll be 47.5. So then to find that little bit that remains, you would do 50 minus 47.5 and you get 2.5. That's one way to do it. Another way is you could look at the breakdown and you're basically adding the bluish color and then the black color together.
Now if I were to say 2 minutes, 10 seconds and longer, like including that, then you would add that whole 13.5%. Like with this being like after 2 minutes, 10 seconds, like after that standard deviation, if it said like that and longer, like including it.
Well, longer would be everything that's in the black that's shaded.
Right, but like if the problem wanted you to like include it, then you would use the entire 13 point.
Then they would give you a different time if they wanted you to include another standard deviation.
Okay. Like
Like they would have said something like 1 minute and 10 seconds. Like they'll give you a different time if they were talking about another part of the graph. The probability that person waits less than 1 minute and 10 seconds for the elevator. 1 minute and 10 seconds is how many seconds? 70. 70 was to the left of your mean, wasn't it?
Yes.
And less than would mean, is that to the left or to the right of that?
Left.
To the left. So it's asking me for what's this probability of basically the shaded region. How much was that?
No, wrong.
As we're looking for left. We're looking for this left part. One thing to keep in mind, your mean is here. Your mean makes up 50% to the left of that. So it has to be something that's less than 50%.
Yeah, 16%.
It's going to be 16%. 70 was at 1 standard deviation. Between your mean and 1 standard deviation, that is 34%. So then you subtract the 2 to get that probability there. What's that as a decimal?
0.16.
Because we're looking for a probability.
Now, I can't remember if you'd already answered this, but it can never be written as a fraction. It always has to be a percentage, right?
No, a fraction and a decimal are probabilities with the percent symbol. That's a
Oh, I
percentage.
see.
Questions? Now, the expected value is something that you may be asked to find, okay? It is found by multiplying the number in the sample by the probability, okay? So, expected value. If I shoot free throws in basketball and I'm a 75% free throw shooter and I shoot 100 free throws, I'm expected to make how many of them? A little louder.
Wait, you got a 75% chance of like
Making a,
got 100 shots, okay, 75,
and I shoot 100 free throws.
75.
I'm expected to make 75. That's how you figure out, okay, well, if they're a 75% free throw shooter, that means they should make, if they shoot 100 free throws, they should make 75 of them. Expected value is found by multiplying the number in your sample, 100 free throws, by the probability. I'm a 75% free throw shooter. So you multiply the 2. You use this to help answer D. It says 200 people are observed and the length of time they wait for an elevator is noted. So wherever they got their mean and standard deviation from, they got it from basically observing 200 people and how long they waited for the elevator. We're going to calculate the number of people expected to wait less than 50 seconds for the elevator. How many people are expected to wait less than 50 seconds? Was 50 on our curve?
It was 2 standard deviations.
It was at the 2 standard deviation mark. Now it says less than 50 seconds. Less than that, is that to the left of that line or the right of that line? To the left.
So 2.5.
So the probability of this is 2.5%. So what's that as a decimal?
0.025.
0.025.
So then if my probability is 0.025 and I see 200 people and I collect their data for 200 people, then how many is expected to wait less than 50 seconds?
5.
And you get that by doing what? You multiply by 200. So 5 people got lucky that when they pressed the button, they only had to wait less than a minute to get that elevator to open up. That's how you use normal distribution to find expected values. That's how you use it to draw normal distribution curves with your mean and your standard deviation. This is how you can also use it to figure out different probabilities and percentages of your data based off of this information. Yes?
If you were to get a decimal for the expected value, would you round down?
You would round down because if it's people or cars, you can't make up for the 10th of a person that's not accounted for. Good question. Now, with this particular example, every one of the seconds that people had to wait were actually on your normal distribution and at your standard deviations. It will not always be that way. To find probabilities when your x value isn't one of the standard deviations, you use your calculator. And what you do is, everybody has their calculator? You press your second button, then you press your bars button, and it'll pull up this screen right here. So press your second button and your VARS button. Does everybody get these options right here? Distra stands for distribution. Distra stands for distribution. Okay? This is where you're going to go for your normal distribution. And you want to go down to option 2, which is normal CDF. Okay? Normal CDF. Now, if your calculator looks like mine, it will pop up these options right here. If yours doesn't, this is exactly the order in which you have to type in your information. Okay? This is the order in which you have to type in your information. So let's take a look at an example, and let's use our calculator to find our different probabilities. The heights of 250 20-year-olds women are normally distributed with a mean of 168 meters and a standard deviation of 0.06 meters. Your problems will say normally distributed or something around those lines to let you know you're dealing with a normal distribution problem. Okay? With a mean of 1.68 and a standard deviation of 0.06. Really quickly, I'm just going to draw out a curve so that way we can see how the standard deviations lie. Can someone add 0.06 to 1.68? Can you add 0.06 again?
1.8.
Can you add 0.6 again? Or 0.06. Perfect. Let's go to the other side. Let's subtract 0.06 from 1.68. 1.62. Let's keep subtracting. 1.56 and one more. This is what your normal distribution curve would look like for the heights of these women. Okay, that's what it would look like. Okay? Now the first question asks you, find the probability that a woman has a height greater than 1.6. Is 1.6 on one of your standard deviations? No. So when this happens, you're going to have to go to your calculator because 1.6 lies in between 1.56 and 1.62. Okay? To get any type of method points for these types of problems, which are going to be strictly in your calculator, you want to draw a normal distribution curve with the value that you are trying to determine the probability of. Greater means I'm going to shade left or right of that line. If you notice, I did this with every problem from the last one. This is how you can get a method point. Because you're letting the grader know that I'm looking for this part, this piece, this portion of the normal distribution curve. The probability that's greater than 1.6. Unfortunately, 1.6 is not one of my standard deviations, which means I have to go into my calculator to find this out. So to do this, I have to press those two buttons again. What were they again? Second VARS. Oops, that was that. Second VARS. Option 2. My calculator pops up like this. Yours may have things written already in them. I mean, I've used this for other classes. Lower represents the lower boundary of my shaded region. Okay? My shaded region goes from basically 1.6 all the way to what value? No, that's just the third standard deviation. It goes beyond that, doesn't it? What number is beyond 1.86? What's beyond 1.92? What's beyond 2? Infinity. There we go. Okay? A really big number. So my shaded region is bounded between a lower boundary of 1.6 and an upper boundary of infinity. You have to represent that in lower and upper. So my lower boundary is going to be 1.6 because that's where my shaded region starts. That's the lower end of it. The upper end is infinity. There is no button, no series of buttons that you can press for infinity. You have to tell the calculator you want a really, really large number. That number is 9, second comma, which is right above the 7, 9, 9. That is basically 9 times 10 to the 99th power. That's scientific notation for a really, really, really large number.
Is that the biggest number possible for the calculator?
That's probably what you would want to type in to avoid any error messages. Okay? So 9e to the 99 represents infinity for the sake of these problems. Okay? That symbol, you've seen it before. What does that symbol mean? So I type in my mean, which is 1.68. And you've seen that symbol before. What does that symbol mean? So you type in your standard deviation. If you notice, I didn't have to press clear. I could just start typing, and it overrides it. Now I go to paste, and I click enter. If your calculator is not like mine, then that's literally the order in which you have to type it in. Lower bound, comma, 9E99, comma, 1.68, comma, 0.06, close parenthesis. Then when you type enter, that is the probability. Round out to 3 significant figures. What is that?
909.
So 0.909. So the probability that out of these 250 women, their height was greater than 1.6 meters was 0.909. So about 91% of the women that they surveyed had a height larger than 1.6 meters.
How many marks would that question
2. Mm-hmm. 1, you get your method here, your answer here. Yes.
If you're looking for the probability of something to the right of the left of 1.6, what would you type into the lower bound?
Negative 9E99. Because you need negative infinity, right? So there you go. All right, but we'll get that because that's C. Okay.
To get the full method point, would you also have to like write the rest of the standard deviations, like the 1.68?
What I did in the pink was so that way you guys can see that these values are not on my standard deviations. Let's look at the next one. Find the probability that a woman has a height between 1.59 and 1.75. 1.59 and 1.75 are not one of my standard deviations. So again, I'm going to have to use my calculator. I draw the curve to indicate these two values, and it's between, so where should I shade? So when I look at this, what's my lower boundary? 1.59. What's my upper? 1.75. So I go where again? Second bars. Option 2. 1.59. 1.75. Luckily enough, I don't have to change it because all my information is still the same from before. So I just go down to paste. Again, does anybody have to actually physically type this information in? Make sure you include the commas if you do. Separate each piece. When I click enter, did we get this number? So 3 significant figures would be
0.812.
There you go. So about 81% of the women that they interviewed were between these two heights. Yes.
If your like little graph thingy looks kind of like bad, like if it doesn't look like if it's skewed or something and it's not supposed to be, do you look at the method points or do you do anything else?
The main thing is that wherever that peak is, that's your mean, wherever that peak is. So as long as a value that's supposed to be to the left of the mean is to the left, and the value that's supposed to be to the right of the mean is to the right, then you're fine. And of course the shading. Yes. Okay. All right. While I work with Guyena, you guys try C.
99, or the scientific notation, but like negative.
So 1.7 is not on my standard deviations. So I am going to have to use my calculator again. And it says less. So is that to the right or the left of that line? So there's my method to indicate I'm looking for this probability. What's the number over here? Is negative infinity. So basically in my calculator, I'm going to do negative 9E99. How do I get the E again?
A second comma.
Second comma. Is that my lower or my upper bound?
Lower.
So negative 9, second comma, 99. My upper is 1.7. My mean and my standard deviation stay the same. Did everybody get that?
Yes.
The more you do it, the quicker that you get with it. But that is how you use your calculator to find your different probabilities. Questions?
Do we do this like handwritten?
So this right here, the normal distribution curves is where you get your method points, but the probabilities are going to come from your calculator. The only time they won't is when it's actually on one of your standard deviations.
So do we use like centimeter paper or graph paper?
No, not for this. This will be like freehand.
So whenever we have to like write our units and all that, would you put like 0.631 probability?
Because this is a probability because it's a decimal. Yeah. But these, of course, you want to make sure that this is in meters, this is meters, and this is meters for your curves. All right. One last thing to go over is just like I used the calculator to find your probabilities, your percentages, your areas underneath the curve, you can actually use those to find the actual x values on your x-axis. So if you're given a percentage area and are asked to find the value corresponding to it, then you use something that's called inverse normal calculation. Okay, inverse normal calculation. This is used when you're given the probability and you're looking for the x value. The last two problems, every time you were given the x value, you were given the height, or you were given the wait time for the elevator, and you had to find the probability. Inverse normal calculation is used when you are trying to find the x value. You're trying to find the wait time. You're trying to find the height, and they give you the probability. Okay? You have to remember, though, especially if you're dealing with an old calculator, the newer ones, the color calculators, you don't have to worry about this next little piece that I mentioned. But for majority of us, we have to remember that it's the area to the left when we're using our graphing calculator. If you're given an area that's to the right, you must subtract it from 1 or from 100%. 1 if you're given a decimal, 100% if you're given a percentage. Okay? The reason why is because you need to, the calculator only does probabilities that are to the left of a particular x value. So you have to let the calculator know that, okay, this is the area that I need you to, this is the area that I'm given, and I need to find the x value related to that. It's always the area that's to the left. Always the area that's to the left. How do you get to this point? It's the same two buttons. It's still second vars, but this time you're going to go to option 3. Option 3 is when you're given a probability and you're looking for an x value. Option 3 is when you're given a probability and you're looking for an x value. When did I use option 2? When you're given an x value and you're looking for a probability. Use option 3 when you're given a and you're looking for a
X value.
Okay.
It's not always written as a probability, though, right? It could be a percentage.
It could be a percentage. Yeah, either probability or percentage. So let's take a look. This is example 3. It says the volume of cartons of milk is normally distributed with a mean of 995 milliliters and a standard deviation of 5 milliliters. It is known that 10% of the cartons have a volume less than X milliliters. Find the value of X. So, we have some cartons of milk whose volume in milliliters is distributed normally. We have a mean of 995 milliliters and a standard deviation of 5. It is known that 10% of the cartons have a volume less than X milliliters. 10% less than X milliliters. Would 10% be on the left of the mean or the right of the mean? To be on the left. So 10% is less than X milliliters. We are looking for X. Okay? And again, it's the area that's to the left of that line because it said less than. Okay? So, it's our area to the left. We don't have to worry about doing any subtraction because it's already talking about that area. Now we just need to find it. So, we go to our calculator, second bars, just like before, but this time, I have to go to option 3, and this is what pops up. Area is the same thing as percentage. It's the same thing as probability. You have to type it in as a probability. What am I going to type in? Point 1, point 10. It's 10%. That's to the left of that line, so I have to type it in as a decimal, which is 0.10. I need to type in my mean, which is, and my standard deviation, which is, then I paste. And that's what I was saying. Y'all with the fancy ones, all you have to do is make sure that you let the calculator know that it's the left area. Okay? Yeah. So if you have those fancy ones, you just do left. So then yours will pop up comma left, and we don't have to worry about that. Then you click enter, and that's your X value. That is the milliliter amount where 10% of the cartons weigh less than that. What's the answer?
Well, no, 989.
989 milliliters. And that's how you find X values. Okay? Let's do one more that deal with that. Let's do part B. Because I know the bell's going to ring and cut me off, so we're not going to be able to get this full problem, but I'll finish the video when you guys leave, but we'll do part B together. It says, it is known that 8% of the pairs weigh more than M grams. Calculate the value of M. On this normal distribution of pairs, their weights, what's the mean? 110. I have a standard deviation of 8, and it's telling me that 8% of the pairs weigh more than M grams. The key word is more than. So is that going to be to the left or to the right of my mean? To the right. And this is going to be shaded to the right because it says more than, and this would be 8%. 8% weigh more than M grams. Questions on the picture?
Would that be your method points?
This will be your method. Now, for a majority of us, not the colored fancy calculator people, we cannot type in 8% for our area. We can only use the area that's to the left. What is this whole probability that I highlighted in yellow? How much is that?
Oh, 92%.
And you get 92% because that's what 100 minus 8 is. We have to do it this way. Otherwise, the calculator is not going to give us the right answer. It's always the area that's to the left. Well, more than lets you know that it's going to be shaded to the right, but what we have to type in is going to have to be to the left. Now, you color calculator people, when it comes to the option, you can put 0.8, you just have to say right. Okay? So let's go to our calculator. Where do I go again? Second bar is option 3. The area, for people like me, I have to do what? 0.92. What's my mean? And my standard deviation was 8. Okay. So it'll be 121 grams. So at 121 grams, 8% of my pears weigh more than that. Okay? But you guys, like I said, you just have to indicate is it to the left or to the right. We always have to do the area that's to the left. Questions on inverse norm, normal distribution, or sampling techniques. So to finish off this problem real quick, it asks us to find the percentage of pears that weigh between 100 and 130. So if I look at the normal distribution curve, 100 would be here, 130 would be here, and I'm looking for everything in between. Because I'm looking for a percentage, that means I'm going to be using normal CDF. So that's second bars, option 2, lower bound is 100, upper bound is 130. My mean is 110, and my standard deviation is 8. So when I paste it all in, my probability is going to be 0.888. That is the probability that the pears are going to weigh between 100 grams and 130 grams. Now for the last problem, it says 250 pears are weighed. You have to calculate the expected number of pears that lay less than 105 grams. So for this, remember expected value, you have to determine what the probability is first and then multiply it by your actual number. So 105 grams is here. We want to see that if they weigh less than that. So then we're looking for this probability here, and whatever we get, we're going to multiply by 250. So we need to go into my calculator and then determine what is that probability. Because I'm looking for a probability, I'm going to be using option 2. My lower bound, that is negative infinity, so I want to make sure that I use a really, really small number. So remember that's negative 9e to the 99. My upper boundary is 105. My mean and standard deviation have not changed. So this is going to be my probability. Now, because I have to multiply that by my number, I just multiply that by 250. And then that is going to be my expected number of pears that are going to weigh less than 105 grams. So that 0.265 number gets multiplied by 250. So then my expected number of pears would be 66. Because remember, we cannot compensate for basically half of a pear that doesn't exist with that decimal, so we do not round up.